Hello and welcome to episode 12 of Modulus Manufacturing's build of the Robotics AR4 Mk3 robotic arm. The robotic arm is now mechanically complete. We have all 6 joints on the arm, along with the servo gripper kit that's mounted to the end actuator of joint 6. In this episode, which is quite the blockbuster, I'll be going through the installation of joint 5 and joint 6, including a couple of side quests which required computer-aided design, 3D printing, and some of those 3D print files I've linked in the description below. Very shortly, in the next couple of minutes, I'll go through the mechanical components of the arm, including showing you how all 6 of the joints rotate and move on the arm. So follow along. I hope that you've been enjoying the build series. If you are, please like and subscribe. So without further delay, I'll show you how the mechanical components work on the AR4 Mk3 robotic arm. So here we have joint 1, joint 2, joint 3, joint 4, which rotates like so. So joint 4, if I turn the arm around, is up the top here. And we have joint 5, which is actually at the front of the arm. So this whole assembly itself is joint 5, whereas joint 6 is essentially the robotic arm gripper or actuator rotating using this joint 6 motor. So that rotates within joint 5. So bringing it back to joint 1. Joint 1 allows the arm to rotate in the X and Y direction. It has no bearing on the Z direction or the height of where the actuator is, but it does impact the X and Y of where the actual end actuator of the arm. Now this can rotate pretty much 360 degrees, so it goes from all the way back here to rotating all the way around until it hits the limit switch at the bottom of joint 1. So I'll wind that all the way around there, and we'll hear just now the limit switch. So that rotates around like so. Then you've got joint 2. So joint 2, which is this joint down here, is driven directly by the joint 2 motor through the joint 2 motor's gearbox and allows the arm to rotate forward and backward like so. As you can see, that would then impact the Z height as well as both the X and Y, because this is moving out into free space. So that's joint 2, that moves up and down like so, and can move from all the way back here to pretty much all the way forward. So you've got over 180 degrees of movement. Following that, we've then got joint 3. So joint 3, which is driven by the joint 3 motor down here, through a belt underneath this cover and up into this assembly, allows the arm to rotate up and down like so at the top of the arm. So we can have the arm quite tall and rotate over, and that's joint 3. And as you can hear, it's also got a limit switch that will measure the end of its travel. So that's joint 3. Joint 4 rotates inside of this turret here and allows this entire assembly to rotate pretty much 360 degrees around the joint 4 turret here. So this entire forearm of the robotic arm, if we can think of joint 2 as the main arm, this would be the forearm, and this can rotate up and down on joint 3, but then can rotate around like so, allowing us to come in from different angles with the forearm. Joint 5, much harder to rotate here for demonstration purposes, but joint 5 moves this end piece up and down. So again, that's about 270 degrees of rotation or more. And finally, joint 5 is the rotation of the servo gripper so that we can rotate whatever we're holding with the hand. So it's almost like just rotating my hand itself. All of these have limit switches that define the end of their travel, but they also have encoders on them for closed loop control. So once we know that end point using the limit switch, we can then define that in software, and we know exactly where the motors are and the joints are at any point in time. So that's essentially how the AR4 Mark III robotic arm works mechanically. Now we're going to move forward on completing the wiring of the arm. The central component of the Joint 5 carriage is this lead screw nut, which comes with the Joint 5 linear motor from Stepper Online. It's made from polyoxymethylene, most commonly abbreviated to POM. POM is known for its high wear resistance, impact strength, and rigidity, which is useful as it's this nut that will translate the rotation of the Joint 5 motor shaft into linear motion. If you're a fan of safe machining practices, please like and subscribe, and I'll try harder next time not to hold things by hand as I drill them. Anyway, the reason that I'm countersinking these holes here using a large 10mm drill bit is to allow these 3 M3x10 flathead screws to sit flush with the top of the POM nut when it's installed into the Joint 5 carrier. So each one of these holes, as you can see here, I just keep testing it to see if I've got the depth correct, and then using the drill bit, drilling into the top with a very high drill bit speed but light pressure to cut away at the top of the POM plastic and make the countersunk holes. Using a proper countersinking tool would also make sense here, but I was working with what I had. Countersinking these 3 holes to the correct depth such that the M3 screw heads were flush with the surface was an iterative process and took a few rounds of drilling, clearing the holes, and then test fitting the M3 screws to be flush with the head of the POM nut. At some point during the process, I did switch to using my vice grips, which meant that I was able to properly grip the POM nut rather than using my hand and drill it with a little bit more force. Unfortunately, using a bit more force and less drill RPMs did lead to some of the POM material splintering off, but I was able to retain the structural integrity of the nut while still countersinking each of those 3 holes. To clean up the holes in the end, I did use the Stanley knife to just cut off any of the splintered POM material, and then once that was done, I was able to fit all 3 M3 screws through the holes. With the POM nut prepared, I get the beautifully machined aluminium Joint 5 carrier from the hardware kit and install the POM nut into it with the countersunk side facing upward. This is quite hard to rotate the POM nut once it's installed into the carrier, so I made sure that the 3 holes that were countersunk lined up with the 3 holes pre-drilled in the Joint 5 carrier. Once this is pressed into place, I then install the 3 M3x10 flathead screws through the POM nut and screw them into the Joint 5 carrier. While working on the previous steps, I had these 2 3mm internal diameter by 20mm long brass bushings in my freezer. I now slide these into the Joint 5 carrier, which has been warmed up in my oven to approximately 60 degrees Celsius, and as you can see, these fit through the entire width of the Joint 5 carrier. Just a quick shout out to Chris Annan from Annan Robotics for the AR4 Mark III kit. The quality of these parts is just phenomenal and all of it comes together quite nicely. Moving along with the build of Joint 5, we now install 4 M3x4 set screws into the Joint 5 carrier to hold the brass bushings in place. The holes for these set screws are pre-threaded, so you just install them into the Joint 5 carrier. Here we have the main structural component of Joint 5, the Joint 5 housing. Machined out of a single block of aluminum, this housing has a large diameter hole at one end that fits over the joint bore tube and a smaller hole at the other end into which we will fit a 608 bearing to support the Joint 5 screw. There's also a large cavity into which the Joint 5 carrier is fitted and will run on 2 3mm linear rods. So you can see the holes pre-drilled for the linear rods down there and the holes for those to be inserted by the 6008 bearing. Logically, the next step is to install the two 3mm diameter linear rods into the joint 5 housing and through the brass bushings in the joint 5 carriage. Due to the orientation of the rods, with one at the bottom and one at the top on opposing sides, there can only be one way in which the joint 5 carrier is installed in the housing. These linear rods are just being lightly fitted at this point to check alignment, and we'll fully install them after adding an M4 screw to the uppermost rod to stop it being pushed in too far and obstructing a hole we require for future use. A hole into which I am installing this M4 screw is used in a future step to mount the joint 5 idler tension block. Installing the screw at this point stops the linear rod from going too far into the hole and preventing the screw from being fully tightened up when the idler tension block is added in a future step. After adding the M4 screw, I can now proceed with the permanent installation of the 3mm linear rods. Using a pair of needle nose pliers, I align the rod with the holes in the joint 5 housing and press them in as hard as I possibly can. Once I've got the rods seated in those holes, I can then turn the joint 5 housing up on its end and use the pliers themselves as a flat piece of metal on which to try and force down the rod through the joint 5 housing. Simply pressing down on it as hard as I can wasn't enough to fully insert that rod, and so I tapped it a couple of times, a little bit gently, but managed to get it in without causing any damage to the joint 5 housing. Of course, we don't want to bend those linear rods, so in a future step, I do make sure that the joint 5 carriage easily moves up and down inside of the joint 5 housing. But at this point, I'm just repeating that process on each side until the 3mm linear rods are flush with the face of the joint 5 housing. Here, I'm applying a small quantity of inox grease to each of the linear rods before manually moving the joint 5 carriage up and down within the joint 5 housing to spread the grease and also run in the brass bushings on the joint 5 carriage. So moving that up and down quite a few times until it's smoothly running within the joint 5 housing and feeling comfortable that it's going to work without getting stuck. Up to this point, everything had been progressing smoothly with the assembly of joint 5, and it was super satisfying to see this complex rotational to linear to rotational movement gearbox coming together. As you can see, I installed two M3x6 set screws quite deep into the joint 5 housing on either side to secure the linear rods in place. Turning the joint 5 housing on its side made it easier to add the second set screw, and once this was installed, I was then able to remove the M4 screw from earlier to allow for the installation of the joint 5 idler tension block. Speaking of the joint 5 idler tension block, this was the first part in this entire project that was supplied by Robotics, which didn't fit straight out of the packet. No matter which way I fitted it into the top of the joint 5 housing, I simply could not get it to fit, and it was more than a couple of microns difference, and given that it's meant to slide within the joint 5 housing, it wasn't something I could just get over by hammering it into place or using a temperature difference to try and get it to fit. So at this point in time, I was a little bit stuck as there was more than just a couple of millimeters required to get it to fit into the joint 5 housing. Thanks to my ultra-fast Bamboo Labs X1C 3D printer, but particularly to Chris Annan, who has actually put all of the structural components of the Robotics kit on his website as 3D print files, I was able to keep pushing on with the build after only 30 minutes with this 3D printed version of the joint 5 idler pulley block, which you can see here being installed into the joint 5 housing. So this part did properly fit, and it was 3D printed using 100% infill ASA filament. And as you can see, easily slides within the joint 5 housing. After ensuring that it could easily move within the joint 5 housing, I then secured it in place with two M3x8 socket head screws. Next up is the assembly of the joint 5 idler pulley itself. This consists of the aluminium joint 5 bearing post on the left-hand side the HK1612 bearing, which was fitted over the top of it, and finally the 3D printed bearing post spacer. You can see here that the bearing then rotates around the joint 5 bearing post. Bringing the joint 5 assembly back into shot, I then install the joint 5 idler pulley into the 3D printed joint 5 idler tension block using an M4 by 14 socket head cap screw, which I then install and thread into the 3D printed plastic itself. Creating the thread in the 3D printed plastic idler tension block was reasonably easy, but required a lot of pressure from above using the 3mm Allen key until the screw gripped into the plastic and then it was able to self-tap. In high spirits, after feeling like I had averted the issue of the joint 5 idler tension block, I moved on to the test fit of the 608 bearing before adding it to the joint 5 housing. As you can quite clearly see, the bearing didn't fit on the joint 5 lead screw and I was getting pretty frustrated. Although mildly frustrating, this is a known issue with the joint 5 lead screw, and really it's a minor fix of filing down the end of the joint 5 lead screw as you see me doing here. The joint 5 motor and the lead screw are provided by Stepper Online and don't reflect on Anna Robotics at all. In fact, it's a big testament to Chris and to Anna Robotics that they've detailed this issue in the build manual and recommended the test fit of the 608 bearing in the first place. Filing down the lead screw doesn't take too long, as the bearing is only fitted onto the very end of the joint 5 lead screw, and so turning it around and filing it allows you to just knock off the ends of the flutes. Here you can see the 608 bearing successfully mounted onto the end of the joint 5 lead screw. Now knowing that the 608 bearing is going to fit over the end of the lead screw, I take the joint 5 housing and input it into the 3D printer, where rather than 3D printing something, I actually use the heated bed to heat the part up to 80 degrees Celsius. This is going to thermally expand the aluminium joint 5 housing and make it easier to fit the 608 bearing into the end of the joint 5 housing when we install it. Using an oven mitt here to hold the joint 5 housing, which is now at 80 degrees Celsius, I very briefly tried to use my fingers alone to press fit the bearing into place in the joint 5 housing. Despite the housing being at 80 degrees Celsius and the bearing at negative 15 degrees Celsius, the temperature differential itself just wasn't going to cut it in being able to press that bearing into place. To do so, I brought my vise onto the bench and then used the mechanical advantage of the vise to press the bearing into place, which was a successful way of installing the bearing. So as you can see here, once we remove it from the vise, you can see that the 608 bearing sits flush with the surface of the joint 5 housing. To more permanently hold this in place, I set it back down inside the vise and then install an M3 by 6 set screw through the top of the joint 5 housing here, which presses down on the 608 bearing and stops it from moving out of place. With the joint 5 housing completed and the joint 5 carriage on the linear rails, it can now be installed onto the joint 4 tube next to the joint 4 timing pulley. This occurs by winding the POM nut in the joint 5 carriage onto the joint 5 lead screw until the lead screw is fully installed in the joint 5 housing and securely lodged into the center of the 608 bearing on the end. You can see here that I rotate this in a clockwise direction, and once it's seated on the end of the joint 4 tube, it makes it much easier for it to be threaded on as it's now being supported at one end of the joint 5 housing. Rotating the arm using joint 2 so that we can see the end of the lead screw come through into the 608 bearing, I continue to wind the joint 5 housing on. Once the lead screw is installed into the 608 bearing, we'll obviously be supporting the joint 5 housing from both ends of the arm, but with most of the forces being taken where it mounts onto the joint 4 tube. So here we can see the joint 5 housing pressed all the way up against the joint 4 timing pulley, with the joint 5 carriage on the right-handmost side, pressed firmly up against the 608 bearing end of the joint 5 housing. Sliding the joint 5 idler pulley block to the right exposes a pre-threaded M4 hole in the joint 5 housing. When we rotate the joint 4 tube so that the motor wires face downward, we can see that there is a hole in the joint 4 tube which lines up with this M4 hole. Into this hole, we install an M4 by 10mm set screw, which mechanically locks the joint 5 housing into place on the tube longitudinally, making sure that it doesn't fall off, and also ensures that the housing and forearm of the robotic arm rotate at the same time as the joint 4 tube and the joint 5 motor, which is attached to the other side of the joint 4 tube on the other side of the joint 4 turret. This means that when the joint 4 motor turns the timing pulley, both the joint 5 motor and this joint 5 housing are rotating at the same time. Here we have the joint 6 main bearing support arm, quite a hefty piece of aluminium. This arm could most definitely have used a weight-saving pocket in the center to lose some mass at the top of the arm, but I appreciate the machining nevertheless. Into the end of it, I installed the tapered outer bearing race of the 30203 roller bearing. Pre-installing a few of the M4 by 18 flathead screws into the joint 6 main bearing arm allows me to easier locate the holes and then hold the arm in place. I'm using a 3mm Allen key to install and tighten all 6 of the M4 by 18 flathead screws, which hold this joint 6 bearing arm into the joint 5 housing. This does add a little bit of weight to the top of the arm, so you do need to offset the arm slightly backward at joint 2 so that it can't fall forward, and then install these. The other way to do this would be to rotate joint 3 into the upward position so that the entire arm faces up, and then that will keep all of the weight over the center of mass. Having installed the joint 6 main bearing arm, which will transfer all the load forces from the payload at the end of the arm, we can now assemble the bearings for joint 5, which will allow this joint 6 assembly to rotate at the end of the arm. The joint 6 housing, machined out of a single piece of aluminum, has 2 shafts, one thicker than the other. Onto this thick shaft, we install the inner bearing race for the 30203 tapered roller bearing, and then apply a generous amount of grease. As you could probably tell, this is the side that will be pressed into the 30203 outer bearing race on the end of the joint 6 bearing arm. To hold the joint 6 housing in place, this joint 6 bearing cap is mounted on the other side of the J6 main arm and rotates using this set of TRA 1625 needle bearings. Unfortunately, the project ground to a halt at this point as I'd misplaced one of the TRA 1625 bearing washers, and I simply could not find it. As you can see here, I went online to find a replacement bearing. Now, the ridiculous part is that it's quite a cheap and well-known thrust bearing washer type. So the cost in Australia, or to get it to Australia, is as low as about $4 Australian, but of course including shipping. Now, shipping from anywhere in Australia, I'm located in Western Australia, so getting it over here is probably a couple of days. So rather than delay the project, I'm able to 3D print a thrust bearing washer, which I'll then fit into the casing, at least as an interim measure. So thankfully, Chris Annan, in his AR4 Mark III robotic arm build manual, does specify all of the bearing types, and also, even though it's an Imperial, all of the bearing thicknesses as well. So moving across into Onshape, I have opened a new SketchUp in here, and I can click on the top plane, which is top, and click N, and this will snap the plane to be perpendicular to the view. I can then create a new sketch, and I'll choose the top plane as the sketch there, and then use a center point circle. This here works on diameter, so I can click here and dimension this here to be 50.8 millimeters in diameter. What I want is 39.67. Now I can have another sketch that I put in the center here, and this bit will come down and I'll click D to dimension it, bring this out and make this 25.4, so 1 inch. That's the center diameter there. I can then accept that sketch, which is fully defined because it's gray, and extrude this by 3.2 millimeters. Once that's done, here we have our TRD 1625 washer ready to be 3D printed. I can then rename this part down here. And I'll export it for 3D print. I can open up the file and add in the TRD 1625 bearing washer. That just sits in the center of the build plate there. And one thing I'm going to do here, because it is going to be under pressure and I don't want it to deform, is go in here and change the infill density to be 100%. I'm also, because I want it to have a nice smooth surface, I'm going to choose a seam scarf, so that will make less of a seam on the outside where it starts. And I'm also going to choose ironing on the top surface. So on any top surface, it will actually go through and add in a tiny little bit of plastic to fill in the lines and make it iron it out to be as smooth as possible. With that sorted, I can now go ahead, slice the plate, which is literally only 16 minutes rather than waiting, a couple of days for a replacement part to arrive, and print plate. So this will send it off to the printer and we can get printing. Less than 20 minutes later, and I had a brand new 1625 bearing washer. As you can see, the dimensional accuracy and smoothness of the print, especially with a smooth print bed and the ironing turned on, is great. Excited to keep moving on with the project, I assembled the bearings in the joint 6 bearing cap, only to realize that I'd printed the thicker 0.126 inch bearing washer rather than the thin 0.032 bearing washer. This resulted in the bearing washer protruding from the top of the bearing cap, which simply wouldn't allow it to work. It was straight back to the virtual drawing board. Thankfully, like most computer-aided design software, Onshape is parametric, meaning I was able to objectively define the thickness and simply change the thickness of the washer by adjusting the extrude value here. After this, I re-exported the new bearing washer as a 3D printed STL file and made sure to note the change in the file name. To bamboo slicer, I'm going to go in here, and instead of this, I'll replace it with an STL. So I'm selecting a different STL here, and that's the 0.032 inch thick one. I'm actually going to copy this and make a few copies just so that we can select from the best copy. I'm also, because we're down to only couple of millimeters, 0.8 of a millimeter, I'm going to do this extra fine bamboo X1. Use these modified values. I'm still using the ironing, I'm still using the 100% infill, but I'm now printing at only 80 microns. So 0.008, meaning that there's going to be 10 layers in these printed parts. When I go to the printer itself, I will also reduce the print speed down to 50%. I can now slice these parts and print the plate. Great success! I like! After getting the project back on track, after successfully printing the 0.8mm thick bearing with ASA filament in just 10 layers of 80 microns, I was able to remove the thicker 3D printed bearing washer from the NTA 1625 needle bearing race from the joint 6 bearing cap. Quite a bit of grease was removed along with that thicker bearing washer, so I took the time to reapply some grease, after which I then added the thinner 3D printed bearing washer on top. As you can see, the 3D printed bearing washer fits perfectly and protrudes just above the outside of the joint 6 bearing cap, so it can rotate easily. It's finally time to assemble the joint 5 bearing, which starts by installing the joint 6 housing
and the tapered roller bearing into the joint 6 main bearing arm. For those of you who are more visual learners, you can now see how the joint 6 bearing cap fits onto the outside of the arm with a central screw that attaches it to the thicker shaft of the joint 6 housing and then pulls the 30203 bearing into place. After testing the rotation of joint 5 and making sure that there's no play in the joint, I remove the temporary screw that was in the center and replace it with this M6x14 socket head screw, which sits into the center of the joint 6 bearing cap. And I found it was easier to tighten it up initially by holding the joint 6 bearing cap in place and then spinning the joint 6 housing on top of it. I then tightened this up, and this holds the whole assembly together. To ensure equal pressure on the NTA 1625 needle bearing, 6 M4x5mm set screws are installed into the outside of the joint 6 bearing cap. These then press against the thick metal 1625 bearing washer, which then applies equal pressure to the needle bearings themselves, and finally onto the arm through the 3D printed bearing washer. And this whole process then applies pressure through the central screw onto the tapered roller bearing, pulling that into the joint and ensuring that there's minimal play in the joint 5 joint at the top of the arm. So tightening all of these M4x5 set screws up, and we can see that it rotates nicely with no play. It's time for some more 3D printed parts, but fortunately this time they're on purpose and very much part of the plan. Here I have the joint 5 side plate printed in a galaxy purple PLA filament, which gives a bimetallic look depending on the angle that you view it from. As you can see here, I'm starting the process of tapping 4 holes at the front of the joint 5 side plate using an M3 tap, and these 4 holes will be used in a future step as we start to assemble the other side of the joint 5 main arm. So this will be on the opposite side from that joint 6 main bearing arm, which we've attached to the robot so far. The process of tapping these 4 holes at the front or circular hole end of the joint 5 side plate is easy but time consuming. Starting each thread in the plastic requires a fair amount of pressure from above, but once started, the threads are easy to form and this part really isn't that thick. After tapping each hole, I then ran an M3 screw through them with a screwdriver just to test that the threads had properly been cut, which concludes this process and allows us to move on. In addition to the 4 threaded holes, there are also 8 rear holes in the joint 5 side cover, which have to be drilled with a 3.25mm drill bit to allow for the 3mm bolts to pass through and into the arm. Like the tapping of the 4 forward holes, this was a simple but repetitive task, and thanks to the plastic being pretty thin, the drilling process didn't cause any issues here. However, unfortunately this wasn't the case for the thicker joint 5 side spacer. Anticipating the future steps of the AR4 build manual, after drilling the joint 5 side cover, I went ahead and drilled the much thicker joint 5 side spacer with the same 3.25mm drill bit. Usually in my 3D printing, I work with engineering filaments such as ASA and polycarbonate that have high melting temperatures. This part, however, was printed with PLA, and the repetitive drilling caused the drill bit to get very hot and start melting the plastic around the holes. It was pretty concerning at the time, as the plastic perimeter looked close to breaking and requiring a reprint. However, by allowing the drill bit to cool between holes and using a Stanley knife to clean up sections, I was able to get away with only minor cosmetic issues to the inside of the joint 5 side spacer. When building your own AR4 robotic arm, take this into consideration and make sure that you allow the drill bit to cool or use a higher temperature plastic filament. With the relevant holes now drilled and tapped in the joint 5 side spacer and joint 5 side cover, I aligned the 2 parts on the top of the bench prior to installation on the arm itself. Coming back to the main assembly of joint 5, the joint 5 side cover is installed with this recessed section near the circular hole facing towards the joint 6 body at the end of the arm. A single 3mm by 25mm long Phillip head screw is then used to hold the joint 5 side cover in place onto the joint 5 assembly. Next up, the XL15 pulley, the last remaining pulley in the AR4 mechanical kit, is installed onto the small shaft that protrudes from the joint 6 housing. I did initially install it the wrong way around, so please note that the pulley shoulder should be facing the camera. It should not be installed the way that you see it on screen at the moment. Before installing the belt and moving the joint 5 lead screw for the first time, I added some additional inox grease to the linear rods and the lead screw itself. It's important that the joint 5 carriage with the POM nut is located right up at the end of the joint 5 assembly, at the end closest to the pulley and the joint 6 body. You can see here how I have the assembly with the joint 5 carriage right up on the right hand side of the screen. Making our way over to the other side of the arm, it's now apparent why we wanted the joint 5 carriage at the end stop, as we needed to make contact with this limit switch from the AR4 electrical kit bag through the slot in that exact position. We make sure that the lever arm of the limit switch is right up on the joint 6 end of the slot, and the switch is inserted so that we can hear the switch close with a satisfying click. To hold the limit switch in place, I use 2 M4x10 set screws installed from the top of the arm, making sure not to over tighten them and squish the switch in place. We will be wiring this in a future step. The final step of assembling joint 5 itself is to install the belt that translates the linear movement of the joint 5 carriage into rotational movement of the joint 6 body. To do this, I drilled a 3.25mm hole in the center of the belt width between 2 teeth, which was a fun one-handed challenge to hold it in place while trying to drill. Once drilled, I was able to test fit the belt between the idler pulley near the joint 4 timing pulley and the XL15 pulley at the end of the arm. In order for joint 5 to work correctly in pivoting the joint 6 assembly at the end of the arm accurately, the tension on the belt here has to be extremely tight. I started the process of installing the belt by fitting it over the XL15 pulley and then over the idler bearing within the joint 5 carriage. I also tightened up the bolts of the joint 5 idler tension block, which was 3D printed out of white ASA filament earlier in the video. To try and help the process, I did loosen off the joint 5 idler bearing bolt inside the joint 5 idler tension block to allow it to pull forward a little bit and then tightened it up. However, in this process, I actually found that the tension on the belt was enough to deform the white plastic within the joint 5 carriage, and I had to remove this entire assembly to inspect what had gone wrong and why the belt wasn't being properly tensioned. After removing this out and seeing the deformation of the white ASA filament, which we will see shortly when I remove the joint 5 idler bearing, I then had to revert back. Now, either I could have printed this out of a much stronger polycarbonate filament, which would have done the trick, even though it's quite a small part, but I actually opted, given the amount of deformation that you can see just around the center of that white idler tension block, to take my file to the joint 5 idler tension block that came with the AR4 hardware kit, and after quite a few minutes of filing, both on screen and off, I was able to finally fit that aluminium joint 5 idler tension block in place. With that in place, I was then able to fit it into the joint 5 carriage, bolt it in, add the joint 5 idler bearing back in place, and finally stretch the belt over the top, following the instructions within the AR4 build manual from pages 176 all the way through to 180. Now that the belt has been fitted over the XL15 pulley at the front of the arm and the joint 5 idler bearing at the joint 5 carriage, it's now time to calibrate joint 5 to an angle of 105 degrees using a 3D printed template. Okay, the 105 degree template. I'm just going to open up Onshape here and start a new sketch. So for the sketch plane, I'm going to choose right, And I'll just go here and I'll set a new sketch plane, and this is just going to be our triangle that goes backward, allowing us to make that. And I'll dimension it by clicking on D, and I'll make it 100 millimeters long, or 75 millimeters long. I'll also make this 15 millimeters high. And then over at the end here, we're going to start a new sketch, and we'll make it like this. I'm going to click here to there until it gets to an angle, and I'll click 105. From here, I'll then extend this line out 25 millimeters. And then finally, I'll bring this down here to about 60 millimeters. I'll then extend this line down. I'll dimension this line to sit at 180 degrees, so make sure it's straight. Finally, bring this across to there vertically, and I can zoom in, and as you can see there, it didn't quite intersect the other line. I can go across here until I intersect that line. Now this area is grayed out, showing that it's a fully defined sketch. And with that in mind, I can go back here. You can tell I'm not an absolute expert at CAD. Perfect. Now I can extrude this. So I can extrude these two parts, make it only 10 millimeters thick. It's really just to measure that. And we've got ourselves a 3D printed template for measuring the angle of joint 5. So I can rename this part, call it joint 5 angle. And once this is done, we can then export this as an STL file, so it can be 3D printed. So I'll click export, export that, and we can exit out of our CAD software. I can jump across into Bamboo Studio here, and now I can go and add this part. Saying yes, and then I'll auto orient this part, which obviously has a nice flat surface to lie down on. And I can also click arrange, and the software will arrange it in the best possible orientation. All of these strength settings are fine, so I'm just going to use the standard strength setting for the Bamboo Lab X1C. And I can now slice the plate. I take only 34 minutes and 13.7 grams of plastic, and click print. This will now send it off to the printer to begin printing. After 3D printing the 105-degree template, I use my ruler on the top side of the joint 5 housing to extend it outward, and then add the 3D printed guide, which sits over the top of the joint 6 motor housing within joint 5. As I haven't yet tightened the set screws in the joint 5 pulley, I can easily rotate the joint 6 motor housing until it matches the 105-degree angle as seen here. You can also see that the joint 6 motor housing has the motor side facing down. This is important that we get this alignment correct before then tightening up the set screws within the joint 5 pulley. And check out the link in the video description for a free download of the template. Now that I've mechanically calibrated joint 5 by rotating the joint 6 housing to an angle of 105 degrees, with the pulley still not having the set screws tightened, I install this joint 5 carrier clamp to the underside of the belt where it contacts the joint 5 carrier, and then thread a M3x8 cap screw through the top of the carrier, through the hole that was drilled in the belt, and into this clamp, which sandwiches the belt and holds it securely onto the joint 5 carrier, so that when the joint 5 carrier moves up and down inside of the joint 5 housing, the belt will actually rotate around the eye of the pulley and around the pulley at the end of the arm. In order to permanently sync the movement of the joint 6 housing with the joint 5 belt's movement, I installed 2 set screws into the XL15 pulley, tightening them up almost all of the way. I then used the 3D printed template one last time to check the mechanical calibration and ensure that it's at 105 degrees. Once I've checked that, I can then tighten both of those set screws up to hold the XL15 pulley in place onto the joint 6 housings post. This will make sure that it all moves at the same time, and if in future we need to recalibrate that angle, we can then loosen off those set screws to recalibrate. With joint 5's belt installed, tensioned, and mechanically calibrated, I remove the 2 placeholder M3 bolts that I had in place and then install the joint 5 side spacer just over the top of the pulley. I don't at this point install the side cover, and because we do need to get access to the joint 5 lead screw for a future step where we'll be moving that joint 6 housing around so that we can install the joint 6 motor. As you can see here, we have the joint 5 carriage, which is this entire section here. This is the joint 5 carriage mounted to the front of the joint 4 assembly, right by the timing pulley. This obviously adds a lot of weight to the arm, so you can see without me supporting it, without the arm being driven, it wants to fall either forward or backward. And you can see there, I just rotated joint 3. So that's joint 3 that rotates and is driven by the joint 3 motor further down the arm. We also have the joint 4 motor here, which rotates this entire assembly around itself. And then you've got the joint 5 motor, which sits behind, helping to balance out the weight of the front of the arm. In here, you can see in the joint 5 carriage, we've got this lead screw that comes through from the joint 5 motor. This goes into a carrier here with a nut inside, and when that gets pulled backwards around these linear rods that are inside, that moves backwards and forward inside of this carrier. That then is translated from a linear motion, so a rotational motion of the motor, into a linear motion up and down that shaft of this, which then gets translated back into rotation by this belt. So the belt rotates around the eye of the pulley here, all the way up to the pulley at the front of the arm, where it then rotates this joint 5. It's joint 5 assembly. This joint 5 assembly has the joint 6 motor installed into it, and that rotates around with the gripper up the front. So it's quite a stiff assembly, allows for high precision, and is also very clever in the way that it moves the weight towards the back rather than having that motor all the way up at the front of the robotic arm. So now that we know how the joint 5 assembly operates, it was time to skip forward and stand the arm up vertically to prevent the forearm from rotating under its own weight. Using a cordless drill and the same 3.25mm drill bit from earlier, I cleared out the 12 holes around the joint 5 side cover and started to install it. To install this, I used 8 M3 by 25 Phillip head pan screws at the bottom of the assembly, the side closest to the joint 4 timing pulley, and at the top of the arm in this shot here, I used 4 M3 by 20 Phillip head screws that screw into the holes that we previously tapped in the 3D printed joint 5 side plate. As you'll see shortly, it was a mistake to add the side cover at this point in time, and I should have followed the manual. After all of the complexity of building the joint 5 assembly, it was on to probably the easiest task of all, which was just using a small tube of superglue to affix the AR4 small logo into the side of the joint 5 side cover. I used the end of the tube to kind of smear the superglue around a little bit, set the arm to be almost flat, and then put the 3D printed AR4 logo into the top of the arm to allow it to set. This was printed out of white ASA filament. Later that day, after allowing the superglue to set, I was back at it again, removing 11 of the 12 screws to swing the joint 5 side cover out of the way and allow me to access the joint 5 lead screw. This was a necessary step as the joint 5 lead screw needs to be turned manually to rotate the joint 6 housing at the end of the arm from the calibrated 105-degree angle down into a 45-degree angle. You'll see here over time that the joint 6 housing at the end of the arm, right by that pulley, is slowly rotating in the shot. And if you go back over the last 30 seconds or so, you will see how it moves from the 105-degree angle up into this 45-degree angle, where we can more easily install the joint 6 motor. Once this was done, I reinstalled the joint 5 side cover. Here we have it, folks, installing the final motor from the AR4 stepper motor kit, the joint 6 motor. In order to install it, I removed all stickers and labels along with these small dust caps that are present just at the interface of the gearbox with the motor. I also removed the yellow cap that covers the shaft and the pre-installed keyway, and then installed it into the joint 6 motor housing with the wires facing upward. You can see here that it fits perfectly in place, the square interface of the motor fitting into the protruding flanges of the joint 6 motor housing. To hold the joint 6 motor in place, I installed 4 M3 by 3 set screws that go into these pre-tapped holes in the joint 6 motor housing. You can see just below the black of the motor, the silver square interface at the bottom of the motor, which fits perfectly into the flanges of the joint 6 motor housing. This is also why we had to turn the joint 6 motor housing around to the position of 45 degrees, so that we could access these 2 set screw holes at the bottom of the motor mount. After tightening up the last set screw, I turned joint 6 back over again, and you'll notice that there are 2 spare holes on the top for the limit switch of joint 6. So we'll get onto that next. Usually at this point in the manual, the 3D printed joint 6 limit contact, which you can see here printed out of black PLA, is added to the aluminium joint 6 gripper mount, as the servo or pneumatic gripper hasn't been built yet. However, if you've been following the channel, you'll see that I got ahead of myself a fair few months ago and built the servo gripper kit, which you can watch that whole process in episode 3 of the build series. To mount the 3D printed joint 6 limit contact block, I used two 2.5 by 8mm pan head screws. Once both of these were installed, it was now time to complete the mechanical assembly of the AR4 robotic arm by installing the servo gripper kit onto the shaft of the joint 6 motor. Here it was, the big moment where the AR4 robotic arm would be mechanically complete. Simply line up the joint 6 gripper mount with the keyway on the joint 6 motor shaft and slide it on. Unfortunately, the arm clearly had one last test for me, and as I tried to wiggle the servo gripper onto the joint 6 motor shaft, it simply wouldn't continue to slide on and actually got stuck to the point where I couldn't pull the servo gripper off of the arm either. So at this point in time, as you can see, I'm not actually trying to push it on anymore. I'm trying to pull it off, and I was unable to dislodge the servo gripper from the shaft of the joint 6 motor. To remove the servo gripper from the joint 6 motor shaft, I used a gas torch on the aluminium joint 6 gripper mount itself, being careful to avoid the 3D printed filament. Once this was done, I used some vice grips on the top of the servo gripper kit and tried to shake the servo gripper free from the arm. Unfortunately, this didn't seem to work, so I ended up resorting to using the vice grips as a form of leverage, using the face of the end of the joint 6 motor to lever the servo gripper kit off the end of the arm. Hopefully this doesn't happen to you, but it is useful to see how I was able to free it from the end of the arm. Once freed from the joint 6 motor shaft, looking down the keyway of the joint 6 gripper mount, I could see that there was aluminium swarf around the point where the set screw enters the keyway. This is quite difficult to get to, and obviously something worth checking yourself before you install it onto the joint 6 motor shaft to ensure that that has been removed. To try and counteract this, I did also press the joint 6 motor key further into the shaft, tried to file it down, and iteratively went through without getting it stuck, and pressed the servo gripper onto the end of the joint 6 motor shaft. Trying this over and over again, I still couldn't get it fitting onto the joint 6 motor shaft, and so I was kind of getting a little bit frustrated here. I used lots of different tools to try and get it on, and it did get stuck once more. At this point in time, it was too wide for the vice grips to fit into place, so I was able to use some needle nose pliers and then use the same leverage technique to remove the servo gripper from the end of the joint 6 motor. After using a very small flathead screwdriver to knock the swarf around the end of the set screw hole out of place, and then some compressed air to remove the swarf from the hole, I was finally able to press the servo gripper fully onto the joint 6 motor shaft. This was a massive step, and I was super happy to have completed the mechanical assembly of the AR4 Mark III robotic arm. It's been quite a few months to get to this point, obviously as a hobby, fitting it in around other projects, and this is really satisfying to see it all go together. Ironically, I ended this entire process by installing the set screw that had caused about an hour and a half worth of issues at the very end. There you have it, the mechanical completion of the AR4 Mark III robotic arm. In the next couple of episodes, I'll be doing all of the wiring, so please like and subscribe, and sorry to all of those who have been waiting quite a long time for this video to come out. Stay tuned, and I'll see you in the next video.